For today, let's continue with predictive modeling. Okay. So last time the week before last time, we started doing this very basic predictive modeling, the linear regression, right? If you remember, we tried to predict medical cost. And that's to predict something, some continuous quantity, right? So cost, price, any continuous quantity. And so we use regression models for those kind of predictions. And then we quickly switched to classification problems. So basically we have a certain label to predict. Right? Last time we predicted whether or not customers are going to, I guess we didn't do that in our notebook, but we actually have an example saying that we want to predict whether or not customer will be making a purchase, right? So that's called classification because there are only a few finite number of possible outcomes for the target variable. Purchase versus no purchase, and that's a binary prediction. Now, today let's continue with classification problems. Last time we discussed the logistic regression as well as the KNN, K nearest neighbors as classification models. So this time we're going to dive into decision trees. We already mentioned decision trees last time, by briefly giving you some main idea underlying this predictive model, right? So let's have a quick review of what we discussed last time about decision trees. So as we know, any supervised learning essentially tries to establish a relationship between features and the target variable, something you want to predict, right? So whether or not a customer is going to make a purchase, and whether or not a patient is going to show up, and for this kind of problems, we always try to establish some relationship between the features and the target variables, right? So based on patient demographics and appointment time, can we predict whether or not the patient is going to be a no-show? Okay, so decision tree is basically one method for us to establish such a relationship, right? Given the feature, how do I map that into a certain label as our prediction for classification problems? Okay, and branching is the main idea, and let's quickly overview the problem we discussed last time. Let's say I want to predict if a customer will purchase a certain product. Let's say after we send the customer the information about this product. Right? So we focused on only two features, age and income of the customer. This is largely only for better illustration in the slides, right? In reality, of course, usually you have more than two features, but it's easier to visualize the feature space if we only have two features. Okay, and the target variable is purchase versus no purchase. And yes is purchase, no is no purchase, or we use the binary outcome variables, 1 and 0. 1 is purchase, 0 is no purchase. Now, if we have only two features, we can easily visualize that on a two-dimensional plot. Right? So horizontal axis is age, vertical axis is income, and every point here basically represents a customer. So for example, a customer here is going to be around the age of maybe 37, and income is somewhere between 20,000 and 40,000, maybe around 30,000. Now, the colors here represents the labels, right? Red are purchases, no are no purchases, blue are no purchases, right? So what we want to do is to eventually, if you have any new customer may show up anywhere on this feature space, right? For example, a customer of 20 years old, income around 60,000, the customer will be somewhere here, right? So at any location in this plot, what I want to do is to predict whether or not the customer is going to purchase the product if I show them the information about my product, right? So how do we do that? The idea of decision tree is that I want to sort of divide the whole space of features into different regions. And then for each region, I will assign a certain label here, either yes or no. Right? Now, the simplest way of partitioning the feature space is, of course, no partitioning. Right? So let's say I don't do any partitioning. So the whole feature space is just one region. And then I will just assign one label to the whole feature space. In that case, what label do you think we're going to assign? Right? Let's say I don't do any partition for now, and then I point anywhere on this feature space, two-dimensional feature space. I want to just predict whether or not the customer is going to make a purchase. How do we predict? Any quick thoughts? Now, for every region, under the decision tree model, we have to assign only one label, either yes or no, right? Now, let's say I have the whole region, and we're not doing any partition. And then for this whole region, we're going to look at the number of yeses and number of no's, right? Apparently, there are no more no's than yeses. So if I don't do any partitioning, instead assign a label to the whole feature space, then I have to predict all the outcomes to be no's, right? Because there are more no's than yeses. I will be more confident in saying no than saying yes based on this data set. Okay? Of course, this is not going to be accurate, right? So that's why we need to do partitioning. So for example, I can choose one of those two features to split the whole feature space into different regions. Right? And you can start with income, or you can try age. Eventually, I want to pick the best one. Right? How do I pick the best one? For example, let's try to split with respect to age. Right? And then I need to choose a threshold. For example, I choose the threshold here, which is about 49 years old. Right? And then I will be able to divide the whole feature space into two regions, right? The left part and the right part. And I have to, now with those two regions, as the outcome of this partitioning at age equal to 49, now I have to assign a label for both of those regions, right? For example, for this region, if I have to assign a label, is it going to be yes or is it going to be no? So yes is red, which is purchase. No is blue, which is no purchase, right? And then looking at the region to the left, which is age below 49 years old, if I only can assign one label to the entire region to the left of age 49, maybe I have to use no, right? Why is that? Because looking at all those data points in this region, much more blue ones than red ones, right? If I have to select a label to represent this region, it has to be blue. I mean, as a result of a majority vote, right? And there's the remaining region to the right of age threshold, 49 years old. And this region, I have to assign a label, which is yes, represented by red color, because in that region, we have 3 red points versus only 1 blue point. So we can simply do a majority vote to label all the region to the right to be yes, to be the yes region or the red region, right? So if I stop here, I already have a prediction model, right? Because you just point anywhere on the feature space. For example, some point here, it's in the blue region, in the no region, so I will predict that person not to make any purchases, right? On the right-hand side, in the red region, if a new customer show up and the income and age of that customer falls into this region, I will predict that the customer will make a purchase. And this is how decision trees can make predictions for us, right? Now, how do I know it's going to be the age feature that we should make the split based on, or should I actually split the feature space based on a certain income threshold? Well, beforehand we don't really know, right? You can choose one of those features, age and income. I try to see what is the possible outcome, right? And the way we're going to determine whether or not we're going to select a certain feature And how we're going to select a threshold for that feature is determined by the impurity of the resulting partition, right? So after I divided the whole region into two parts, I want to see how pure are each of those two partitions, right? So the purer the better, because in each region, eventually I want to select a certain label to represent the whole region, right? So then if a region is predominantly having data points belonging to a certain label, and then I will be more confident in casting my prediction, right? So for example, in the red region, looking at those data points, 3 red points with only 1 blue point, I guess I can say that for any customer there, we are sort of confident that that customer is a yes, red color, roughly with a probability of 75%, right? Because 3 red points versus only 1 blue point. So basically, the impurity of each region is going to be determined by how many yes labels and how many no labels you actually have in that particular region, right? So let's get down to some quantitative calculations just to better understand the idea of using impurity measures to see how pure are each of those regions, right? The more pure, the better, because eventually, if a region only has blue points, and then I would be more confident in voting blue for any new data points showing up in that region, right? So we have the formulas for 2 impurity measures. Gini index, entropy are the two mostly commonly used impurity measures. So the formulas themselves are not as important, but it's still a good idea to maybe try to understand their meaning. So let's actually do some quick calculations. Okay? And then once again, let's say I divide the whole feature space into 2 parts, left and right, based on age threshold 49. And let's see how will the purity or impurity measures look like for both the left region and the right region. Okay? Now, let's look at the left partition first, right partition first. Let's look at those 4 points, right? So 3 red points and 1 blue point to the right of the age threshold, 49 years old. Right? So what we can quickly calculate will be that, first of all, we calculate the fraction of yeses in that right region. And apparently it's 3 over 4, right? Because 3 red points and 4 points in total. So 3 red among the total 4 points to the right. So it's 3 over 4. 3 over 4. And then the fraction of no's in the right region, right now we focus only on the right region. Okay? It's 1 over 4, right? Because 1 blue point out of the total 4 points in the right region, right? So we have the fractions of the 2 labels in the current region of interest. Okay? Now the Gini index says that I can apply the formula, which is 1 minus the fraction of 1 label squared, and then further minus the square term of the other label in terms of the fraction, right? So it's going to be 1 minus 3/4 squared, and that's the fraction of yeses, and further subtracting 1/4 squared. 1/4 is the fraction of no's, and then this is the final number we get, right? 0.375 is the Gini index for the right partition to the right of age threshold 49 years old, and that's the Gini index for that region, right? We can do the same thing for the left region. If we do the left region, we look at all those points to the left of the age threshold 49 years old. We check how many yeses do we have. That's 2 yeses, right? 2 red points. Out of the total, if you count it, it's going to be 16 data points to the left of age threshold 49 years old. So it's 2 out of 16. That's the fraction of yeses to the left of 49 years old, right? And fraction of no's, it's 14 out of 16, right? 14 blue points to the left of the threshold out of the total 16 points. So we know the fractions of yeses and no's, and plug those 2 numbers into the Gini index formula, and then we can easily calculate the value of the Gini index for the left partition only to be 0.219. Okay. So now question, we have two numbers, right? If you remember, the previous number for the right partition is 0.375. That's the Gini index value for the right partition. Now we said the left partition has a Gini index of 0.219, a slightly smaller number. Question, is the left or right partition more pure? So what do you think? I mean, the purer the better, right? Because ideally, I want a region to have only one type of data point so that I will be more confident to say that this region will have the prediction equal to the predominant data points. So what do you think? This region Gini index is 0.219. This region to the right is 0.375. Which region is more pure? Well, the idea is that the Gini index is an impurity measure, right? So if the larger the value, the more impure. So based on those numbers, the Gini index of the left part is 0.219, smaller than the 0.375 on the right-hand side. So the right-hand side has a greater Gini index, so it's more impure. And this is actually also intuitive, right? Because you see, even though like in this region apparently red is dominating, but 70% of the points is red. And on the left region, blue is dominating, but the fraction of blue points among all those points to the left is a higher fraction. Right? It's actually 14/16 for the fraction of blue points, and that's I guess 87.5%, which is kind of higher. So the left-hand side is more predominant by the blue points compared to how predominant is the red points to the right-hand side. Right? So this is just a quick illustration. And then if you calculated the impurity measures of the left region and the right region, I want to construct an overall impurity measure combining the two spaces, right? So we have those two numbers as the Gini index for left and right partitions, and we need to somehow combine them together, right? So one quick way is that we can count how many points in the left region, so that's 16 points, and how many points on the right region, which is 4 points, right? And then we do a weighted average. Add up those two numbers after multiplying by the number of points, and further divide by the total number of points, which is 20 points. And that's what we call the overall impurity measured by Gini index. Right? And you can easily calculate the final value of the overall impurity based on Gini index to be 0.2502. And that's what comes out if I choose the age as the feature to split. I also have chosen the threshold, age threshold, as 49 years old, right? And what you should do is that for age, I can try all those different possible thresholds, maybe 20, 30, 35, or anything possible. Okay? And then for every split, I calculate the overall impurity measure. Okay? I will choose the one that gives me the lowest impurity measure, and that's the optimal split. Okay? And same thing for other features. You can do the same thing for the income. Do I split? If I do split income first instead of splitting on age first, and then what is the threshold? Is it 20,000, 60,000, or 80,000? Try different possible values to see the resulting impurity value. And then how do I choose which feature to split on and which threshold to use? It all boils down to which method of splitting will give you the lowest impurity measure. And that's the one we choose. And turns out if you try to work on this example, 49 years old would be the optimal split, right? So if you split on age 40 or you split on income level 10,000, I mean, either of them is also feasible, but then the resulting impurity measure will be higher. And we want to have more pure outcomes for your split. So that's why the first step of splitting will be based on age 49 years old. Okay, so that's how this example of decision trees work. Let me know if you have any questions. So the main idea is clear. Okay, that's great. And then, this is an example. If I split at age 46, you can do exactly the same analysis. You will find that the Gini index is 0.32, which is a bit higher, so it's more impure. So it's less favorable, right? So that's why our previous split based on age 49 is better. Okay. Now, after I split it based on, let's say, age 49, which is the optimal first split, I now have two regions, right? Typically, we don't necessarily stop after performing a split. So now we have two regions. I will think about whether or not and how I should split the right region further into two subregions, right? And same thing for the left-hand side, right? Further split the subregions. The idea is that if I have chosen another further split, it should be hopefully minimizing the overall impurity as a result of this further split. Okay? So you can keep the splitting process going on, and eventually, if you want, in this example, you can partition the whole feature space in a way such that eventually every region is pure. Right? But last time we mentioned that it may not be that desirable to do a lot of splits. Eventually, every region is pure. Why is that? Anyone still remember why we don't want to do a lot of splitting? Eventually, every region is pure. Well, one quick reason may be that sometimes you keep splitting, and then eventually there may be regions where there are only 1 or 2 points, right? And then for that region, you are making a prediction based on only 1 or 2 points, which is not very reliable, right? So big data tells us that if you have made your prediction based on a lot of data, it's more reliable. If it's just a couple of data points, it's not that reliable. Something we will, something known as overfitting, which we'll discuss a bit later on in today's class, but that's the main idea, right? So, for this example, after splitting at age 49, then let's say I want to further split the right region, and you can try, but I think the best one is to separate the red points with blue points so that we have pure regions coming out of the further split, right? But sometimes we don't really want to split it all the way down to the case where every region is pure because of the reason we just mentioned, right? So that sometimes we may impose restrictions on splitting. For example, one possible restriction is that if the data points in a region is less than a certain value, for example, let's say it's less than 3 points, I don't do any further splitting, right? And then this split is still okay because I split the right region which had four data points, but after this split, I will no longer doing any splitting for the right-hand side, right? Because if I further split, I will have to pick a region containing less than less than or equal to three data points, which is not desirable according to this restriction I impose, right? On the other hand, you have a lot of data points to the left of this age threshold, 49 years old. You can do further splitting, but then eventually, if you impose this restriction of not splitting anything with less than 3 data points, you will find that eventually you will end up with all the subregions to the left-hand side to give you the same label. So in that case, as a quick demonstration, we don't split that region as well, right? So let's say we have performed 2 splits. And then this structure, this partitioning process can be represented by a tree structure. Now, we started from the entire space, and we choose age to make the split. And the threshold is actually 49 years old instead of 40, but the idea is similar. Okay. Now, it results 2 regions, which will represent 2 nodes in this illustration, right? So age less than the threshold, age greater than threshold, and then turns out if we do have this kind of pattern as my eventual partitioning, right? So to the left, we don't do any further splitting, and then we just check the predominant label in that region, which is blue, and blue is no, right? So we predict that in the left region, below the age threshold, the prediction is no, right? For the right region, we have a further split. In this illustration, we actually split based on income level around 40,000, right? So we're going to split based on income level 40,000. There are two possibilities: income greater than 40,000 and income less than 40. So that's corresponding to the horizontal cut to the right of the age threshold, right? So then the income below that threshold of 40,000, it's blue, so it's no. And income above the threshold, we're going to predict yes, right? So that's why after further splitting an income level, the left region where income is lower, the prediction is no. The right region, income is higher, and we'll predict yes in terms of whether or not the customer is going to purchase the product. Right? So this is resulting in a tree structure. That's why we call this model a decision tree model. Okay? So the idea is that we start with the whole feature space, and then we choose a feature, and we'll split based on a threshold for that feature. That results in two subregions. And this is for a certain subregion represented by a node in this structure. If I don't do any further splitting, I stop there. I assign a label to that region. And this is something we call a leaf node, right? Because there's no further branches, right? If I further split a certain subregion, which is a node, and then it will result in further subregions or further subsequent nodes. Right? Eventually, whenever I stop, it's called a leaf node because I will directly assign a label as my prediction for that region. Okay? So that's the main idea. If you know roughly how decision tree works, that would be great because I think it's better for us to apply a model that we somehow understand the intuition of. Okay? Questions at this stage? So some discussions about whether or not we should grow a full tree. Typically, maybe no, right? Because as mentioned, you may end up very few data points in a certain node or in a certain region, right? So restrictions such as that we don't split a node if it contains not many data points, or maybe require that every resulting leaf node, the node I don't further split on, should not have a certain should not have too few data points, right? Let's say every leaf node should not have less than 10 data points. Right? If I do the splitting, and the splitting will result in a leaf node that contains fewer than 10 data points, I will not consider that split at all, right? Sometimes when I actually get a tree after a certain branching or splitting process, I may go back to prune that tree, to cut off some of the branches to make the tree smaller. And this is another strategy that prevents us to get a full tree, because full trees typically will have overfitting problems. Right? So there's a parameter we're going to deal with called cost complexity path, which is something that controls how you would go back to prune the tree to make it simpler. So as we'll see later, there's some parameter called CCP that we can control to determine, somehow influence the complexity of the tree. Okay? Now, there are some other strategies, as I mentioned, to stop early instead of reaching a full tree. Anyways, the key idea is that we don't want the tree to be too complicated, right? So we don't want to have a full tree where every region is pure. All right, so let's say we have this tree, right? And let me slightly change it because we don't really have the right threshold here. Age threshold should be 49 instead of 40. And everything else is okay, right? And let's say now we have this tree, right? Now I want to make predictions. That's the eventual purpose of building a model, right? So that we can use the model to perform predictions. So a new customer shows up, 30 years old, income is 80,000, right? And whether or not the customer is going to purchase the product, right? Or sometimes when we talk about classification problems, we want to talk about the probability of the outcome being 0 or 1, outcome of being purchase or no purchase, right? So 30 years old and 80,000. And if we go back, 30 years old is actually below the age of 49, right? So the prediction will be no based on this decision tree. Okay? And if you are further interested in the probability, we can go back to the feature space, right? 30 years old, 80,000 will be some point around here. And for this point, it's in the blue region, so it's a no. But what is the likelihood of customer choosing no purchase? Well, you look at what's going on in this region, right? So we have 14 blue points, 14 no's out of the 16 data points. So the chance of the customer in this region not purchasing the product can be calculated as 14 over 16, or 87.5%. Okay? So that's how this prediction model works. All right? So there's a bunch of hyperparameters of the decision tree, where hyperparameter is something not part of the parameter that is going to be adjusted by the model during the fitting stage or training stage. Instead, you have to specify those parameters before you can actually train the model, right? So it's a long list of hyperparameters, so let's not worry about that now, and we're gonna worry about those hyperparameter values when we move on to the notebooks for building the model and use the model to make predictions, right? A decision tree model is actually quite interpretable because it's easy to understand that you're partitioning the whole feature space into regions. And why do you assign a certain label for a region? Because the label should be the label of the predominant class in the data set, right? Within that region. So it's intuitive, but then people have shown that the performance is not that reliable. If you do decision tree, typically it may result in poor performances. So people started thinking about how to improve based on the decision tree models. And one idea is to build something called a random forest. Okay? And a random forest is basically a set of trees, right? Because if you predict based on only one tree, empirical evidences show that it's not that reliable. So how about you construct several trees to make it something like a forest, and ask each tree to make a prediction. And then you can average over all those predictions by different trees. So you are predicting based on a number of trees. Intuitively, this will be somehow more reliable than using only one tree. Right? So we know how to construct a decision tree, right? Which is basically to partition the feature space into smaller regions. Now, how would you say we can construct a forest of multiple trees? Any guess? Well, remember, if we have a set of data points, we can put them on the feature space and then starting doing partition based on the location of all those data points in the feature space. And that's how we can construct one tree. But how can we construct multiple trees? Typically we only have one data set, right? Let's say the prediction of purchases versus no purchase. We have a bunch of customers. In the record, some of them purchased, some of them did not purchase, right? And that allows me to construct tree. But how do we construct multiple trees? And then some technique called bootstrapping. But this is essentially the same idea as what we have mentioned as sampling with replacement, right? So we have this original data points. Let's label them as 1, 2, 3, 4, 5. I mean, this is not a class label, but just to give an ID to every data point, right? Now I can create another sample data set based on this original data set. How does this work? Remember, it's just to take those data points in a randomized way, right? Imagine that you have a bin, and then you just take balls from the original data set to put in your bin. And it's called sampling with replacement because once you take, let's say, the data point number 1 represented by a ball labeled as number 1 ball, right? So if I take it usually it's gone, right? But it's called sampling with replacement. I will just replace it with an identical ball, number 1, so that I still have this ball number 1 in the original bin, in the original data set, right? And then I take a second ball. There may be some duplications because by chance I may take the number 1 ball again, and then let's say we take number 3 ball twice, followed by number 5 ball, and that constructs a sample, right? So here what I have done is that take 5 sample points based on the original data set. You can take 4 data points, 3 data points, it doesn't matter, as long as you can have an adequate number of data points to form a sample. Okay? So we have sample 1, you can do the bootstrapping. Once again, for sample 2, for sample 3, let's say you can take 100 samples. Okay? Now, in this way, you created 100 samples. Each sample will be including a few data points for you to construct trees. Right? If you construct a tree based on 1 sample, that's 1 tree. Now you have created different samples based on bootstrapping. Let's say 100 samples. You can construct 100 trees, right? And then later on, you can let those 100 trees to make prediction based on any new data points. Right? So if you have 100 trees, you will be able to have 100 predictions. And eventually, we can aggregate all those predictions by those 100 trees to make the final prediction. Right? So for example, let's say out of the 100 trees, for a new customer, 70 trees predicted that the customer will not purchase. The remaining 30 trees predict that the customer will purchase. And we simply do a majority vote, right? So the final outcome, final verdict is that I predict the customer will purchase the product because for those 100 trees, 70 trees predicted yes, 30 trees predicted no. So we do a majority vote, right? So this is the mechanism underlying random forest. And for random forest, there's some additional hyperparameters on top of the hyperparameters of individual trees, right? Because you need to construct trees. And then you also need to construct the forest based on the different trees. And we're gonna worry about that a bit later. So we have some time before the first break. Now let's just quickly get started with today's notebook where we have an example to demonstrate how to construct a random forest and how to use that method to make predictions. Right? So if you go to Avenue to Learn, go to Content, and under Lecture Materials, select the module Predictive Analytics, and the notebook we're going to use is here. To the right of this bullet point named Tree-Based Methods for Classification. So we have the deck of slides I just showed you, and we also have the notebook. Right? So you can click on that to access this notebook. And on my end, I need to open it with the right account so I can edit it. All right, so let's get started. For this example problem, we're going to handle using random forest. Right? Now, let me quickly explain the context of this problem. Okay? Very simple problem. So we know that when we make purchases, especially online purchases such as buying from Amazon, sometimes we return the product, right? Because maybe it's broken, maybe because it doesn't meet my expectations, so I need to return it. With a generous return window of 30 days or so, many customers will return that product. Right? But for companies, it's important for them to have some idea about whether or not a customer is going to return a product. Right? Because if they do return, you don't get the money. Instead, you have paid the shipping cost to ship the item to the customer. Eventually, they return it, so you don't get any money, even though you have incurred some cost, which is, something important to keep in mind when you are developing your business strategy, or at least have some idea about your profitability, right? So we're going to predict whether a customer will return a product they have purchased, okay? And we start from a data set. And let's try to quickly load that data set as a Python data frame. So this time I included many codes in the notebook while leaving some blanks there, so we can actually focus the most important things in today's class. So because we have repeated we have already created the procedure for building predictive models, right? So we don't repeat all those steps we have completed before. Instead, we'll focus on the new materials for today's class. So you can simply run the cell. It does nothing else but just to load the data and show a few records on the top of this data set. Right? So let's try to quickly understand what's going on here. It's a simple data set with a total of, I think, 8 columns, right? And the first column is the transaction ID. Let's imagine that every row is an order. You have an ID for that order, right? And then for each row, it's a certain order. And then we actually try to figure out what is purchased in that order, right? That's the product category. Of course, you may have different products in one order, but let's simplify matters. Let's say that every order is only one type of product, right? So for example, the first record is for some home product, maybe some, for maybe some plates, right, or other stuff, typically in the home category. And location is the location of customer, where the customer is living in when placing the order, right? And how many items were ordered, and what is the price of the item, whether or not the customer applied a coupon for this order, right? And return last year is a number to show you how many returns the same customer has filed in the past year, so that I can get some idea about how likely is the customer going to return the product this time, right? And the final column is returned. It's 0 or 1, right? 0 is no return, 1 is return. So basically something like a target variable. Okay. Now, let's move on. Target variable is whether or not customer returned, and the remaining variables is going to be the features, except one column. Which column should not be the features? Something, I guess, somehow obvious, right? The transaction ID, which does not contain any information, that's not part of the feature because it contains no information about the target variable outcomes. Okay, some explanations on the different feature columns, except, I included transaction ID as well, but we're going to drop it. Okay, and you should check for missing values, possible duplications, and outliers, whether or not the purchase versus no purchase records are balanced, right? Last time we said that if we have unbalanced labels, and more yeses than nos, and that can potentially cause a problem for the accuracy, not accuracy of the model, but the how useful the model is going to be, even if it may have high accuracy, right? Now let's skip those, because for the current data set, it's actually well structured. It's a balanced data set with returns and no returns after some pre-processing, right? Now let's try to split the data. So first step is to split into X and Y, right? Features and the target variables. Again, I have included the code because it's kind of standard, right? So Y is the target, so we choose the return column. Every value is 0, 1. 0 is no return, 1 is returned. And X is the features, but we do want to drop 2 columns. Transaction ID, which contains no information, and also the target column, right? Because target column is already separated out as Y variable, and then we drop it in the features. We also drop transaction ID, and then after that we can run this cell of codes, and then we can preview the features and the target variable. Right? Features are shown here. Quick observation: we have categorical variables. We also have numerical variables. As you know, we have seen last time, we're going to handle them differently, and the target variable is whether or not they have returned. So it's a binary outcome. Right? Now, the next step is to do the train test split. Now we have the features and the target variable, but we don't want to use every number or every piece of information for training, right? We want to reserve something for eventually testing the performance of the model. And the key idea is, as usual, we have to train the model based on a certain data set, but later on when we try to test the performance of the model, we want to use data points not already seen by the model during the training phase. Okay, so this is nothing new. Basically, we have x and y, and text size is 0.2. This means that we're going to reserve 20% of the data points as testing data, right? And random state being any number you want to use. So basically, this shows that, this is to make sure that you can reproduce the result, right? Because if you don't specify a random state, it's completely random. And next time you do the same split, it's not going to be the same thing, same split as you performed last time, right? If you set a random state, as long as you use the same integer number, the split will be the same, even though it still appears to be randomized. Okay, so we can run this cell, and then we have split x into x train, x test, y into y train, y test. Something similar as before, and just a bit more to set up for our subsequent analysis for today's class. Now, same thing as before, right? We want to build a pipeline. The first step in this pipeline is going to be some data pre-processing, right? For categorical variables, I want to perform one-hot encoding. Numerical variables, I may or may not want to perform scaling. Okay? So here, no worry about the details, but to save some time, let me just quickly mention what I'm doing here, right? So first of all, I separated the column names in the feature part of the data into two lists, right? Cat calls is the column names for the categorical variables, and num calls is the names of the columns corresponding to numerical variables, right? And then the column transformer says that for categorical variables, let's perform one-hot encoding, same thing as before. In this example, I'm not doing anything for the numerical variables, right? Remember last time we said that for distance-based models such as KNN, k nearest neighbors, it's necessary to do scaling. But for many other methods, including regression models and the decision tree models, it's not that necessary. Okay, so I'm not doing anything to the numerical variables. Instead, I'm only doing the one-hot encoding for the categorical variables, and that defines the column transformer as part of the pipeline. And now we're going to define the random forest model as another part of the pipeline. Eventually, we're going to throw both the column transformer and the random forest model into the same pipeline, and that pipeline can be used to fit the data and make predictions. So this is the structure of pipeline. We have used it before, right? So basically, we have a pre-processing stage where we want to somehow transform some of the columns, and then we include a machine learning model. Right now, we're going to include random forest model. Okay. Now, we have already completed the pre-processing part, which is the column transformer. Okay. And now we're going to build the random forest model. And then we're going to combine them into the same pipeline. And then we can perform training and prediction based on this pipeline. Okay. Now, a forest is a certain number of decision trees, right? We mentioned the decision tree model. There's a way for us to construct a decision tree model in Python. But then I think it's better to directly start with random forest, because if you only use one tree in the forest, and that's basically reducing to decision tree model, right? Now let's, for the current focus, let's say we're using 100 trees, okay? And then we're going to define a random forest model for 100 trees, and we're going to specify the values of certain hyperparameters to define how we are going to construct a tree. So we have this sklearn.ensemble library. Ensemble is a class of machine learning models, including decision tree models. And later on, we're going to quickly talk about gradient boosted trees, which is also part of ensemble model. And this kind of model basically combines multiple estimation models or prediction models, and then combine the prediction of the components and eventually give you a final prediction, right? So we want to import this function called random forest classifier. This is to apply random forest to perform classification problems. And the construction process is pretty straightforward. So model equal to, model is the name of the model you created. You can say random forest model or any name you want to use, right? Model equal to random forest classifier. By default, it will specify some of the hyperparameter values for you. But this time, let's make it a bit more, concrete. Okay. Let's quickly walk over some of the hyperparameter values that shapes the structure of the tree. Okay. And also the forest. So first of all, number of estimators. That's how many trees you want to use, right? Every tree is an estimator. You want to combine the prediction by all those trees. So number of estimators equal to, let's say, 100. Okay, that's one hyperparameter. And there are other things we can use. For example, one thing is called, it's already hinted by Gemini, but let me type it just that we can explain the concept along the way. Criterion equal to, let's say, Gini. You can use, other than Gini, you can use entropy, and those are the impurity measures, right? When we are splitting the regions, we want to come up with a split that results in relatively pure subregions, right? And the way we measure impurity is based on either Gini index or entropy. So right now we are choosing Gini index to measure impurity. So that's what the meaning of the criterion. And then maximum depth. So let me specify that as, let's say 10. Okay, maximum depth is 10. So depth of a tree is very intuitive, right? So let's say you have a tree. Let's say you look at this tree here. The root node is on top. It's upside down tree, right? If you travel from the root node all the way to the farthest leaf node, we count how many steps do we need to take, right? So for this tree, from the root node to the farthest leaf node, I have to travel 2 steps, right? 1 and 2. So the depth of the tree is 2, right? Now, we said that we don't want the tree to be too complicated. So that's why we are typically we will specify a maximum depth of the tree. So don't create a tree of a depth exceeding 10 so that it does not become too complicated, right? So let me just use the tap function to specify those 2 parameters. Minimum number of samples for splitting is 10, and minimum number of samples for a leaf node is also 10. So basically we are saying that if the number of data points in a region is less than 10, we don't further split that region, right? So this also help us restricting the complexity of the tree. And min samples leaf equal to 10 specifies that every leaf node in your tree should have at least 10 data points. Okay? Otherwise, I will not do any branching that leads to any leaf nodes with too few data points. A leaf node is a node in the bottom of the tree where you don't further branch on it. Okay? And then there's another parameter, CCP, cost complexity path, alpha equal to, let's say, 0.01. Right? And this one is used for pruning the tree. Once you have grown the tree, you want to go back to cut off some branches to make it simpler, right? So if this number is larger, and then you are enforcing a simpler tree, right? And the details are not so important, so let's not actually worry too much about it. And finally, random state. Let's say random state is 42, right? Or any number you choose. This is because whenever you are doing the branching process, the model will automatically build in some uncertainty, right? So the split is based on the principle that I want to create as pure subregions as pure possible, but it also includes some random splitting or random branching, to optimize the performance of the model, right? So the branching is actually random, so that's why we need to typically include a random state, so that every time we construct the same model, the outcome will be the same. Okay, So this is mostly for reproducibility. So this is basically how we construct the random forest model, right? So pretty simple. Just specify how many trees and complexity of every tree determined by things like maximum depth and how many data points do you want to have for splitting a region, or do you want to have in the leaf node corresponding to a region you don't further split. Okay, and let's actually run this cell, and it's completed without any problem. So basically, this cell creates the random forest model, right? I mean, of course, it's not trained yet, but it's created. Now, going back to the pipeline, we have created the pre-processing step as a column transformer, and then we have built the random forest model. Then we can combine them to form the overall model we can use to train and to predict, right? So the way we do it is that we first use this command. So I have to specify the steps, right? So this is the pipeline, which is the function imported from the pipeline submodule of this sklearn library. And in the pipeline, we have the error message because we didn't specify what to include the pipeline, right? So let me just use the pap function. We just need to specify the steps, right? So first step is the column transformer. The variable name for that column transformer we constructed is CT. And preprocessor is the name of the step. You can use any other name. Okay? And the model is simply the name of the second step, but the operation or the component is the model. And the model we have defined is the random forest model, but we simply call it model, right? I mean, if you call it, for example, RF, and then in the pipeline, you should include RF as your model. Okay? And this constructs the pipeline. So the pipeline is constructed, right? As we can see, there's a volume transformer, which includes the categorical variable operation, which is one-hot encoding, right? And then the next step is to apply a random forest classifier, and that's a model, right? And then once the model, the pipeline model is trained, the color in this illustration will be blue. But right now on the screen it's a bit pinkish. Actually on the notebook it's actually some kind of a light orange color. It means that it's not trained yet, right? It's defined but it's not trained. But in any case, we have built a structure that we can use to perform training and prediction. Okay. Now let's do the training, right? So the training is extremely easy. We have done this before, but let's do it again. So pipe is the pipeline model we have constructed. It's not trained. To train it, we just need to fit it to the data, right? But which part of the data was training data? Right? Features, X train in the training data, and Y train is the target variable part of the training data. So basically, this tells the pipeline to establish a relationship between X and Y. Okay? Of course, you will first perform the pre-processing on the features as well. So it's just a one line, and then after training, we want to just preview the structure once again. Okay? So this is done, and now you look at the same diagram representing the structure of the pipeline model. You see that the color of the boxes are blue. It means that it's actually trained. Okay? Now after training it, it's basically done, right? And all we want to do next is to evaluate the performance of the model. The model is trained, and we can make predictions, and then we can see how good are those predictions, right? And I have included the same old thing for doing, prediction based on the testing data set, right? So first of all, you will use the pipeline model. Its name is pipe. To predict on the test data set, right? To get the prediction of the target variables, and we call it Y prediction, right? Now, Y is the prediction on the feature values in the testing data set, but it's not going to be the same as the reality. There's always going to be a gap, right? Y test is the actual labels in the testing data set. So we compare the prediction by our model, YPRED, with the actual labels in the target variable in the training data set, y-test, and then we can get all sorts of performance measures. One thing we can construct is the confusion matrix, and something we have done for logistic regression, right? And another thing we can do is the classification report. Both are functions that help us generate the performance measures that compares the prediction of the model and the actual labels in the data set, right? And we run this code, we just get the results. Right? So we have the confusion matrix on the top and the classification report containing the measures including precision, recall, F1 score, and accuracy, right? All those metrics we have mentioned before. So this time we're not going to dive into the details again, but the general idea, of course, is that if you have larger values, larger precision, larger recall, larger accuracy, it's better, right? Now, looking at those numbers, it's not so impressive, right? Because precision is basically in the 60% range. Recall for the negative label, which is no return, is okay. But for return, it's actually barely 51%. It's actually slightly, tiny bit better than random guess. So it's not that impressive. Okay. So later on we will see that after some, other operations, we do get some better results. And let's save it for a bit later to see how it works. Right. But this is basically the key idea of the prediction. And then I have included another block of cell. Let's again not worry about the details, but let's run it. Basically, this is to show you that we can get the individual scores. I mean, we have accuracy, precision, recall, right? And we can call upon the individual functions from the sklearn.metrics library to get the performance metrics, right? So instead of showing them together in a classification report. And what we have here is accuracy score, precision score, recall, F1 score. And this is one thing we mentioned last time, which is a fairly important performance measure for assessing the performance of classification models. So what do you think is missing? Anyone still remembers? Other than those scores. Another important performance measure to measure the performance of a classification model. So what is that? So it's the ROC AUC score. It's the area under the curve when you show the ROC curve, right? Receiver operating characteristics curve. Again, a larger value will give you a better result. So let's import that ROC AUC score function and finally do a calculation. AUC equal to ROC AUC score. And once again, we want to compare the actual labels in y-test and the predicted labels in y-pred. Okay? And then finally, let's also print out this AUC score. So AUC equal to the value of AUC score. And let's keep 4 decimal places. Okay. And this is the value is shown here, right? About 64.64%. So that's the AUC score. I mean, last time we mentioned that if it's above 70%, maybe it's largely acceptable. Of course, it depends really on the context, right? But if it's above 80%, that's pretty good. But now it's actually not so impressive. Okay. So, any questions about this part? We have quickly run through this notebook, part of this notebook, because the idea is pretty simple. Right? We know how to build a pipeline. Typically, we have components like pre-processing and the prediction model, right? And what we did here is simply to implement the random forest model as a classifier, and then we can use the pipeline to train and make predictions, and we also assessed the performance of this pipeline. That includes random forest as the predictor. Questions? All right, so now let's move on to the next part, which is closely related, but there's some important issues whenever it comes to any machine learning or predictive model, of course, we always care about the performance, right? Now, there is this fundamental question. We have seen many models. Some models are simple, some models are complex. Okay? Like KNN, k-nearest model, the concept is really simple, right? And linear regression is also often considered as a simple model as well. So, fundamental question, is it better to use a simple or complex model? Right? So linear regression versus, for example, random forest, which is somehow complicated, right? Because in a random forest, you have many trees. In every tree, you have a branching process eventually leads to many branches. So that's a complicated model. About linear regression or KNN, that's a simple model. Is it better to use a simple or complex model? Or I should say, what are the pros and cons for simple models? And what are, the advantage or disadvantage of a complex model? So what do you think? Well, complex model is, of course, often desired, right? Because the model being complex means that it can capture more realistic situations, right? For linear regression, it uses a linear function to predict the outcome. But what if the nature of the problem is not linear, right? The relationship between the quantity we're going to predict and the feature variables, what if the relationship is not linear? And then we'll have a problem, right? So for complex models, it's more flexible. I mean, there's a way for me to adjust the model so that it better fits the data. So complex model is always more capable of fitting the training data. Okay, so a decision tree with the large depths, with many branches, that's a complex model, right? A model uses many features versus just a model uses just a couple of features, right? And that's a complex model, okay? A highly nonlinear model like random forest and neural networks, those deep learning models, they're very complex, okay? And simple models, of course, sometimes is not sufficient, right? Because it's too simple, right? So if you are doing simple models, and then there's some inherent bias, right? Because, well, the model is simply too simple. It does not reflect the reality, okay? So the performance is typically, if it's too simple, it's typically bad on both training and testing, right? Because the model is too simple. It's not the reality, right? And the bias is large because, what is the bias? Bias is basically the gap between the true situation and the simplified model, right? So model is always a simplification, but if it's too simple and the gap between your model and the true relationship between features and the target variable is going to be very different. So that's what we call high bias, okay? That's something we call underfitting, and underfitting is the result of using a model that is too simple. And using complex models turns out also have disadvantages. So what do you think is the disadvantage of using model that is too complex? So I have some descriptions here, but I guess it will take a few moments to digest the idea here. But anyone has any simple intuitions on why some complex models may not be so good in terms of performance? And when complex models may possibly give you bad results. Well, complex models allows you to include a lot of details, right? In general, it's good, but it's only good when you have a lot of data, okay? Let me give you one example, which is an example of overfitting, and that's also an outcome of using an overly complex model, right? So let's say we're predicting the weather outcome, specifically whether or not it's going to rain, right? Based on the main factor, which is humidity. And we know that it's more humid, maybe it's more likely to rain, right? If you look at those the data in this table, right, it actually shows that if humidity level goes up, it is more likely to be raining, right? So if you have a model that predicts whether or not it's going to rain based on humidity, it seems good, right? Because you only use one prediction feature, which is humidity, which is reasonable, right? However, if you decide to go for a more complex model, so for example, let's say you also want to use day of the week. Is it a Monday or Tuesday or Thursday? Does that have some impact on the outcome? And you may have a problem, right? So if you included one more feature for a prediction, it's more complex, right? But it may not serve you well, because if you look at the data, by chance, the 2 Thursdays actually have higher humidity, and it eventually rained on those 2 Thursdays, right? And if you look at this data set, if don't let the model know the context, right? It's very tempting to conclude that on Thursdays it is going to rain, right? Because that's what the data tells us. If you construct a model that says on Thursday it's always going to be rain, on this training data set, the accuracy will be 100%. Because obviously it's working very well in this model, right? But the model is not going to be useful. Imagine that you get another set of data points as a testing data set. Very likely, Thursdays are not going to be more likely to have rains than any other day of the week, right? And the testing performance is going to be poor, right? So what is the cause of this problem, of the bad performance of using one more feature to make the model more complex? It can achieve 100% accuracy based on a model that does not make sense. And what's the problem there? What's the underlying main issue here? Well, first of all, we don't have enough data, right? So we only have 4 data points, 4 rows in the data set, and there's randomness, right? Because those outcomes in those 4 data points is very random. It's just a small sample from the whole population, right? So it contains a lot of random noise. And then with a very small data set, using a complex model, it amplified the random noise. But by chance, 2 Thursdays are raining, that's actually contains some random noise, outcome of some randomness. But the model captured this randomness and amplified it, right? And that makes the model not serving your purpose in terms of the actual performance when you test it on new data, right? So that's the main problem. Let's say, imagine that you have 1,000 data points, 1,000 days, right? And then you will be able to see that, well, on all those Thursdays, it's actually not going to be the case that it's more likely to rain than other days, right? Then you don't have a problem. But if you have a small data set, then the small data set is highly random, right? And then the randomness is captured by your overly complicated model, and that caused a problem. Okay? So what are the disadvantages of overfitting? Using complex model. It causes overfitting, right? And that's basically most of the time because something we call high variance. Right? Variance means that if you test the model on the different training data sets, the results will be different, right? Because if each time you have a small training data set and there's a high degree of randomness in that small data set, and then makes it the situation that the different training data sets will be very different. And turns out you apply your model, you fit your model to those random training data sets. Because the model is very complex, it's very capable of fitting the training data very well, and turns out it has very different outcomes on the different training data sets. And that's what we refer to as high variance, as a potential issue for using complicated models. It leads to overfitting. Okay, so that's the main idea. Any questions? Yeah, hopefully you get some intuition about this, right? Simple models are maybe good or may not be good. The good thing is that it's simple, right? It does not fit every model, every training data set very well, but it turns out it reduces variance. Okay? But then it's too simple. Sometimes it doesn't reflect the reality. But using a complex model amplifies the randomness in your training data. Right? If your training data is small, and then it turns out to be very random, and the random noise being amplified will give you bad outcomes when you use the trained model on real data. Okay, so that's some quick discussion about overfitting versus underfitting, complex model versus simple model. Okay. This is the typical demonstration of using complex model and simple models, right? So for using a more complex model in this plot, if you go from left to right, it means that you're increasing the complexity of the model. Typically what happens is that it fits the training data better and better, right? But the testing performance after a certain threshold of model complexity, it will start to become worse, right? So overall, it may not be desirable for you to make the model too complicated, especially when you have a small data set, right? And it's not desirable to have an oversimplified model, because if the data shows a clear nonlinear trend, it may not be a good idea to use the linear model, right? But it's also undesirable to use a very complex model that can be very flexible, fits the training data very well, because it doesn't generalize. So a balanced approach is going to be good. But how do you decide if the complexity of the model is too much, or is it about right? How do you come up with a balanced level of complexity? It's not a trivial question, right? But what is the main idea? Well, the main idea is that we can simply fit different models, simple models, complex models, try everything, right? And we look at the performance on testing data set, right? The data not seen by the model. If the performance is good, and then it's a right balance. If the performance is not good, it's not a right balance. But in terms of testing the performance of a model, of course we have the train test split, right? We test on the test segment of the data. But there's also something we can use to do better in terms of testing the performance, right? This is something called cross-validation. We have solved the whole procedure here, but let me quickly mention the idea. Right? So imagine imagine that this square is representing a data set, okay? And what we did before is to split the data set into train and test data sets, right? So, so far we have been doing only one split, right? One training set, one testing set. But there's this strategy called cross-validation, which somehow make better use of our data, right? So out of one data set, I can get multiple testing data, so we can test the model multiple times. For example, typically this is called k-fold cross-validation, but let's explain what is a 5-fold cross-validation. You can have 6-fold and 10-fold, or any number of folds, right? So if we focus on 5-fold cross-validation, we are segmenting the data into 5 equal portions, right? So one data set, now it's 5 equal parts. Each part has the same number of data points, right? Now, I can choose any single fold out of the 5 folds as my testing data set. I'm going to highlight it in red color. For example, I can choose the first fold, which is 20% of the data, as my testing data. And the blue folds is going to be my training data. So I can train on those on the 4 folds, the training data, and then I test it on the red portion, the testing fold, right? So I get one train test split, and then I get to train the model and test the model once. Okay? But I can also choose the second fold as my testing data, and the remaining 4 folds combined will be my training data. Okay? And then I get a different train test split. I get to test and train the model one more time. Okay? And I can also choose the third fold or fourth fold or the last fold as the testing set, the remaining as the training data, right? So in that case, out of one data set, I can train and test the model 5 times, right? So eventually I have 5 testing performance metrics. Performance result. Let's say we'll focus on something like accuracy, right? I will have 5 accuracy scores out of this 5-fold cross-validation. I can take the average of those 5 accuracy scores out of this 5-fold cross-validation process. Eventually, if you're averaging the performance measure across several runs, it's generally more reliable than doing just the one training and one testing instance, right? So that's the idea of cross-validation. We don't just split the data once. Instead, I can split it, let's say 5 times or more times, right? And then I can test the performance multiple times. It's going to be more reliable. And that's the whole idea of cross-validation. Now let's go back to the same notebook and let's quickly perform the train test, cross-validation part. We have completed constructing the model, right? So we don't have to worry about it anymore. The model is constructed, which is the pipeline model that combines pre-processing and also the random forest model. Now, in order to do a cross-validation, what we are going to do is first to define a strategy. And it's quite simple. Usually we just need to decide how many folds, right? Is it 5-fold or 10-fold cross-validation? So let's define, first of all, notice that we have imported the function, 2 functions. One is called k-fold for defining the cross-validation strategy. Right? And then eventually we're going to run the cross-validation procedure using this cross-val score function. But first of all, let's define a strategy called kf, and that's defined based on the k-fold cross-validation. Right? And there are several parameters we need to specify. First of all, we have an argument called n underscore splits. So let's say it's equal to 10. So we're doing a 10-fold cross-validation. Okay? And then we're going to specify shuffle equal to true, because the data is going to be segmented into 10 folds in this example, right? But what happens if the first fold tends to be containing only labels of ones? That's not desirable, right? Because then, we're testing the performance exclusively for those testing data containing only 1 labels instead of any other labels, which is not good. So before I really divide the data into different folds, I want to shuffle it up, right? So shuffle is true, so that when I create a fold, that fold does not contain predominantly a certain class of label, okay? And then finally, random state, because of the shuffling, which is to change the order of the data points in a data set in a random way, so it's randomized, right? So for reproducibility, we want to specify random state, okay? Now, this is how we define the k-fold strategy, k-fold cross-validation strategy. But then next step is that we're going to use this strategy to do the cross-validation, right? So we're going to use the function called cross-val score, but of course we have already imported that function, so we can use it, right? And then remember we have a pipeline, right? So that's pipe. So because we always need to test the model based on a certain machine learning model, here the pipeline model, and perform cross-validation based on that model. So specify the model is the first step. And then not only the model, but also the data, right? So you want to segment the data into different folds, but what is the data? X and Y, those are the feature and the target data. And then CV equal to KF. I mean that the cross-validation strategy is what I just defined, right? And then eventually, we need to specify a score, right? Because eventually, for each step of the cross-validation, we have the train and testing data. Once I test the data, I want to give the performance according to a certain performance metrics, right? So for classification, usually a good scoring mechanism or criterion is going to be ROC AUC. So it's the AUC score, right? And this part is optional, but here to be more efficient, we can specify number of jobs equal to -1. This -1 means that you create multiple instances, multiple threads for this function, right? So that you are using all the computer cores to run this procedure so that it's more efficient. Because there are many steps involved, I want to make it as efficient as possible. Okay. Now, let's run it. But after running it, what we can do is that eventually we want to assign an outcome to this cross-validation function. So scores equal to this function, meaning that we're getting the scores stored in this variable called scores, right? It's the AUC scores. And eventually I want to visualize the scores. So let me include the name of the score variable in the end of the code cell. One error. So let me quickly see scores. So let me quickly try to see if I can fix it quickly. So basically it says that, where is it? Sorry, a typo. Number of jobs. It's actually not n job, but it's I'm missing an S. So now let me run this whole block of cells. In the back end, it simply try to come up with different train test splits. For every split, we'll come up with a performance score. Right? Now you can see that this array, this list, we have 10 numbers, right? Because we have done a 10-fold cross-validation, it means that we have split the data 10 times into train and testing data. For each split, we come up with a performance score, which is the AUC score, area under the curve score. Now, it looks much better, right? Even though in the previous performance test, when we didn't use the cross-validation strategy, actually we get AUC score. If you still remember, it's actually about 64%, right? But this is looking much better, right? So because the model, training and the testing of the model is somehow random, right? So even though you get a bad score out of one testing, it may not be reflecting the reality, right? According to this 10-split, 10-fold cross-validation, turns out we're getting much better scores, right? So it's more like a systematic way of performing training and testing, and the numbers you see are more reliable, right? And if you want, you can, typically something interesting to us is that we're going to calculate the mean value of all those scores as a criterion to determine the overall performance of the model, right? So let's run it. Again, so eventually we'll get the mean score, right? So scores is a list of numbers. If scores don't mean, simply calculates the average score. So average score is 75% for AUC, which may not be super good, but it's actually somehow acceptable, right? So this is a cross validation, and some explanations here. Do we have any questions? Okay, now we know how to more systematically and reliably test the performance using cross-validation. And the next topic, somehow closely related, is called hyperparameter tuning. Remember when we constructed a tree, right? There are hyperparameters, such as the maximum depth of the tree, and minimum number of data points in a node, so that I will consider further splitting the node, right? How many trees in the random forest model, right? So all those are something we call hyperparameters. Right? Unlike model parameters are going to be adjusted and fitted by the model, right? For example, which feature do you split at the first step, right, in the random forest model? And for linear regression, what are the coefficients? It's going to be adjusted by and found out by the model. Hyperparameter is going to be given to the model before you can even start training and testing. Okay. Some examples of hyperparameters for KNN, number of neighbors, is a hyperparameter. Decision tree, random forest, how many trees, depth of a tree, minimum data points in every node for splitting, minimum data points in the leaf node, right? Those are hyperparameters. You have to specify those before you can run the model. Okay? Neural networks, which we don't have much time, but we will try to peek into this kind of models as the state of art machine learning techniques next time. But then there are a lot of those kind of hyperparameters, especially in those very complicated models, right? So let's say you have decided to use a tree, and we did use a tree last time, right? So just before the break. So if we quickly go back, we'll see that I specified all those hyperparameters. And then I train the model. But how do you know whether or not those hyperparameters are good values, right? If you change the hyperparameters, you can get very different outcomes, right? Hopefully, we can find an outcome that maximizes your performance, and that's always the case. So how do we do that? And this part is called hyperparameter tuning. So what does it mean? I have showed you two of the many possible methods for performing hyperparameter tuning, but the idea is pretty simple, right? So we just consider a certain set of configurations of hyperparameters. For example, do I use 10 trees or 20 trees or more trees, right? Or do I use maximum depth of each tree being 5, 10, or 15? I mean, you can include more values, but let's consider a simple setting where we only consider 2 possible numbers of trees and 3 possible numbers of maximum depth of your trees. And then we have a total possibility of 2 times 3 equals 6 instances, right? Maybe we have 10 trees, maximum depth is 5, or have 20 trees, maximum depth is 5, or we have 10 trees, depth equal to 10, right? All those 6 different possible combinations. What I can do is that I can come up with a set of hyperparameter combinations. And for each configuration, I will test the performance, right? And then eventually I compare the performance to choose the best hyperparameter configuration, and that's considered as the best model, right? I mean, this is somehow limited because, because of the computational power. Ideally, I want to try and test every single possible combination of hyperparameters, but that's not possible. So I can just come up with a few reasonable settings and test all those reasonable settings and choose the best one that comes out of it, right? So before the next step, next break, let's actually quickly try to run through the procedure of hyperparameter tuning. So this is cross-validation, it's done, and then hyperparameter tuning. Some information in the notebook. I mean, you can try to find some time to read it if you are able to. But I'm just quickly walking you through this tuning procedure. And the main function we're going to use as an example is called grid search CV. Right? So the name suggests that we're going to use a grid search. So we're going to define a grid. And the points on the grid will be corresponding to the different hyperparameter configurations. And then the performance evaluation part is going to be based on cross-validation, right? Meaning that we're going to do multiple train test splits and calculate the average score under each hyperparameter configuration. And eventually we'll pick the best one. Right? So the most important part is actually how to define the parameter grid. It's simple, but it's essential, right? So here I have picked 4 possible hyperparameters. Now one thing to keep in mind, the name of the hyperparameters should be consistent with the name of the parameters in the functions, in the models, right? First, for example, in the random forest model, n estimators is the number of trees. Right? But you also need to add a prefix because we're working on those hyperparameters in the pipeline model, right? The pipeline model has 2 steps, pre-processing and model step. And so model _, n estimators is basically the combination of the name of the step in the pipeline and the name of the argument in the random forest model. Okay? So the way we can do it is that we define a list. So let's say 100 and 200. So I'm going to test 100 trees and 200 trees, okay, for the number of estimators. And model criterion, we can define a list. So remember the impurity measure is what we call the model criterion. So we have Gini index, we also have entropy as the 2 main metrics for impurity, right? And model maximum depth, let's say 5 is a possible value, or 10. I mean, ideally you should try more, right? But it's going to be time consuming, so I'm just trying a couple of candidate values. And then model minimum sample at the leaf nodes, how many data points you require for each leaf node, let's say 3 and 6. Okay? So that's how we define a grid, just the possible values of the different hyperparameters. right? And then after we have done this, let's move on to quickly identify, not identify, but to construct, construct the instance for the hyperparameter testing procedure. Right? Let's call it grid search. So it's a searching procedure, and it's equal to grid search CV, right? And then I need to include a number of parameters. So estimator is the model you are going to use, right? Because you need to specify a model before you can tune the hyperparameter of this model. Right now, our main model is the pipeline model that combines random forest and the pre-processing step. And then param grid, that's the grid of hyperparameters you want to search. It's equal to param grid. So the argument name is param grid, but we also defined an instance of param grid, so specifying the search, the space of searching just a moment ago, right? And we also need to do CV, so specify the cross-validation strategy, similar as what we have done before. Right? Let's do a 5-fold cross-validation. Shuffle the data before you split, and use a random state for that function, right? And then scoring. So when you are doing the cross-validation for calculating the performance score for each hyperparameter configuration, we need to specify a certain performance measure score. So let's use AUC score, right? And number of jobs equal to -1. Okay? And finally, there's something called variables equal to 1, meaning that when you're running the searching procedure, any information in the backend may be shown on the screen, so that you can better keep track of what's going on, right? So let me quickly run this cell. So there's no error. That's great. This is for setting up the search, right? So we have defined the grid of the parameters, hyperparameters for you to search, right? For each hyperparameter, you choose a few candidate values, and then I will test all those candidate values. And then define the search procedure. Basically, we're specifying the model, the cross-validation strategy, because every time I will just evaluate the performance using cross-validation, doing an average score. Now, before the break, one last final thing. Let's try to run this command. Grid search, the searching procedure we defined, and try to fit it to the training data. So it means that we're going for the training data, we're going to test different hyperparameter configurations and eventually pick the best one. Right? We run grid search.fit. I mean, we're fitting it on the training data. We're still saving the testing data for testing purposes, but for the training data, basically, I'm going to divide training data into different folds and test the performance multiple times, and then eventually I compare the scores that comes out of the cross-validation procedure for different hyperparameter configurations. Now, after fitting it, we can try to check the results, right? So how do we check the result? First of all, grid search is something we used as the name of this searching process. Now the searching is over. One thing we can quickly examine is the grid search dot params underscore. Usually, all those sklearn functions, their attributes typically ends with a underscore. And let's run it. So from this result, we can see we landed on a specific configuration of the hyperparameters, right? So it's basically the model suggests that it's better to use entropy as the impurity measure. It's better to consider 10 as the maximum depth of your tree. And minimum samples per leaf, that's 3. And it's better to use 100 trees than 200 trees, right? Remember, there's always a trade-off between model complexity, right? If you use too many trees, that makes model overly complex and sometimes may hurt you. So this is the best hyperparameter configuration. We can retrieve it from grid search, the procedure variable that represents the process of the searching over the grid, right? And that's the best parameters. Of course, this is not the true best parameter, just among those parameters configurations you tested, that's the best combination. Okay, so that's how we can get the best parameters. Also, there's let's do this. Let me remove this. So this another, attribute inside the searching process variable, grid search. It's called CV results. If you run it, it's going to give you a dictionary structure, right? So it's not very easy to visualize. So let's convert it to a data frame. So pd dot data frame. Okay, and let's see what happens here. So basically, here we have a total of 16 rows, right? So basically, what happens is that we have all those candidate values. Eventually, we have 16 different possible combinations. So every row is a specific configuration of hyperparameters. And let's focus on the first row, right? So it tells you about the time consumed by testing that configuration. So that's not super important. But then it also tells you what is tested, right? We tested Gini index as an impurity measure. Maximum depth is 5. Minimum samples at every leaf is 3. So that's one specific configuration. And then we have 5-fold cross-validation. So we have 5 performance scores coming out of those five train test splits, right? And then you take the mean value. It also calculates the standard deviation. But eventually, what is being compared across all those possible configurations is this column of test score, right? Which is the AUC score for the different hyperparameter configurations. And eventually, the model has selected the one with the higher performance score. Okay, so that's what's going on behind the scenes. Okay, and after you have run this searching process, one thing useful is that you can instantaneously retrieve the best model, right? Because for every configuration, it's corresponding to different model, right? If you have different hyperparameter values, it's a different model, and then you can just use grid search, this process instance dot best estimator and assign it to a certain model name. Let's call it best model, right? And that's the that's a random forest model. More specifically, it's the pipeline model that includes a particular random forest predictive model as a component, right? Now we can here I define a dictionary to represent a new data point. Actually, two data points, right? Let's say we have 2 more transactions, and the first it's a listed dictionary in the JSON format. So basically, the first dictionary is the first new data point where the transaction is about purchase of books, and the customers in the city area. 2 books were ordered, price is 100, did not use a coupon, and that customer returned 3 times last year, right? And then the second customer record is represented by another different dictionary, right? So let's quickly do prediction for this new data point, right? So let's make it a data frame. So let's say df_nd, so new data point, to make it a data frame. So pd.dataframe, and then this list of 2 dictionaries as the two new data points will be called new data. Okay, so that's defining the new data as a data frame with 2 rows, right? And to predict, I will do y predict equal to best model, right? We have to retrieve the best model and give it a name as best underscore model, and then I can simply predict it. Okay, so I just predict the performance. Predict the outcome for those 2 new data points as a data frame, and eventually let's do y pred. So the result is 1 and 0, right? So it's a list of 2 numbers, 1 and 0, but we have two new customers or 2 new transactions, right? So the first new order, the predicted label is 1, so that customer is likely to return the product. And the second predicted label is 0. It means that the second customer in this new data point set is going to be predicted as no return, right? So that's how it works. So the idea is pretty simple, right? We have searched over different configurations. You can eventually land on the best model that gives you the best score in terms of here AUC, right? So that's basically the whole procedure of performance testing in hyperparameter tuning. Do we have any questions? All right, so now we have a little bit left for today's lecture materials. But let me see where we have it. So I think I have it in a different file. Allow me one moment. So going back to the previous set of slides, but I think it's not this one. Here. Just to carry on a bit more about some other possible models for doing prediction based on trees. So far we defined decision trees and the random forests, right? So basically it's called ensemble method because we have multiple trees. But there's another class of ensemble methods called gradient boost trees. Okay? It makes prediction based on multiple trees. So that's why it's also an ensemble model. But it uses sequential structure, unlike the random forest, right? Random forest is to say that I bootstrap to create multiple data sets and I construct multiple trees at the same time in parallel based on those bootstrapped data sets. But boosted trees is based on the idea of gradient boosting. And let me quickly explain in a very intuitive way. It's a sequential procedure, right? So basically, I will first construct one tree to provide a baseline prediction. But let's call it tree 1, okay? But we know that tree 1 is not going to be 100% accurate. Right? So actual result is going to be tree 1 plus some error. And the error represents the gap between the actual situation in the data set versus the performance of the tree of tree 1, the prediction by tree 1. There's a gap, right? The gap between reality and the model is error or residual. Okay? Now I'm going to construct another tree. So how should we construct another tree? Using a sequential method. Well, we have tree 1. It's not going to be very accurate. We said that different trees typically don't have very impressive performances, right? Eventually, we'll have some more or less some error. Typically, it's quite large. Right? So this gradient boosting method says that what if I can come up with another predictor, another model to predict the gap, right? Predict the gap between tree 1 and the reality. And then if I can do that, let's say I use another tree called tree 2 to measure the gap or to approximate the gap, right? And then my prediction can be updated as tree 1 plus tree 2, right? The intuition is simple. Tree 1 is the baseline prediction, but there's some gap. That gap is approximated by tree 2 after I fit the tree 2 to this residual, right? So tree 1 plus tree 2 should be a better approximation. But you don't stop here, right? So you have tree 1, tree 2 combined as a predictor, a predictive model, but there's still going to be some error, right? Because you can never be 100% accurate. Now, how about I approximate this error part by using another tree, right? To use another tree to predict the residual. So you have tree 3 or tree 4, so on and so forth, right? So that's the high-level idea of how you would construct a gradient boost tree. I mean, the name is somehow complicated, a mathematical term, but the idea is simple, right? Now, of course, there's some tricky, slightly, complications. Something called the learning rate. So it turns out I don't typically directly add up all those trees, the results by the trees, but we'll multiply the outcomes by tree 2, tree 3, tree 4, all those trees by a certain parameter, eta, and this eta value is basically to adjust the adjustment by all those subsequent trees, right? Because sometimes you just directly add up the result by the trees, typically because the trees are not 100% accurate, and this again may leads to some issues. So typically you want to use a eta value, which is typically smaller than 1, right, to make the impact of the subsequent trees a little bit less. Right? And it turns out this typically have some better results if you treat it as a hyperparameter. Okay, so this is. So let's quickly return to the notebook, and we have just a few remaining steps. So to implement the gradient boost trees, there are actually two main methods. One is called XGBoost, and it's been tested extensively and confirmed to be a in most cases, a good method for you to get high accuracy results, right? So I already outlined the function to construct a XG boosted tree. Pretty similar, actually. One slight difference is that you have to specify the objective. As a classifier, right now we're doing binary classification 0, 1, right? But for XG boost, if it's a multiple class situation, let's say you're predicting, return, not return, but there may be a third label which says that maybe, even if it's not return, you have to issue some refund, right, without return, something situations. If you have multiple outcomes, you have to use multi-soft prop instead of binary logistic, but it's not too important here. So number of estimators, basically how many trees you want to construct in total, right? So let's throw in some random numbers. So let's say 300. Maximum depth, let's say 4. Learning rate is the eta value multiplied by to the different parts, right? So learning rate is equal to 0.01, and this is some parameter called subsample. Let's do it. Let's make it 0.8. Let me quickly explain. So it means that each tree, because we have multiple trees there, right? Each tree will see 80% of the data, right? So I don't want to let each tree see all the data, because sometimes this again causes overfitting, right? And there's another parameter called call sample by tree, and this is, let's say, also set it to 80%. And this means that each tree will see only 80% of the features. Okay, and random state and number of jobs, that's something similar quantity as before. And then let's run it. Next step is that we can incorporate in the pipeline the same thing as before, so I won't explain much. And finally, you can. So this time the pipeline is different because the model component is different, right? So I give it a different name. It's called pipe XGB. So to represent the XG boosted method. So let's predict on the test set, and then eventually generate the classification report, and let's view the content of the classification report. Right? So yeah, this is, I guess, like more or less similar to the performance of the random forest method, right? But I mean, this is actually slightly, I would say slightly, maybe somehow better, because we accomplished those 70% range performance scores for different measures, even without cross validation or hyperparameter tuning, right? So I think this is relatively, we can say that's relatively satisfactory performance.